Hello everyone. In this video, we are going to simulate power voltage transmission system. By doing simulation, let's try to understand what are the conditions to be satisfied in order to achieve maximum power or voltage transmission. Now our system looks like this. So on our left, what we have is the source, and on your right, what we have is our load. And source is consist of voltage source and its output impedance. So here voltage source is represented as V1 and output impedance of the source is represented as RS. So then we have these our transmission lines, and then we have the receiver load. So load, simply we have load resistance. Now the objective is to find suitable load resistance in order for us to achieve maximum voltage or power transmission. Let's take a look at a little bit of theory behind that. So maximum voltage transmission. So let's consider the potential drop across this resistor as VRL. So if you look at this carefully, so this is a potential divider circuit. This RS resistor and RL resistor, they are connected in series. So basically we are looking at the voltage at this point. So we can write VRL equals V1. So this is the source voltage V1 times RL, that's a resistance over here, divided by the summation. Since this is a potential divider circuit. So now next thing is we need to find the condition to be satisfied in order to get the maximum value of VRL. So V1 is a fixed value, so that we can't touch. Only thing is that we can change things over here. So I will divide numerator and denominator with RL, so that I'm getting 1 divided by, say, 1 plus RS divided by RL. So if I want to maximize this one, so what I need to do is this section I need to minimize it. To achieve this one, what we need to do is we need to make RS smaller and RL larger. So when RL is sufficiently large compared to RS, this RS divided by RL, this component reaches to 0. So when they are 0, we can say VRL tends to V1 if this condition is satisfied. So if this condition is satisfied, so we are reaching VRL equals V1. So in general, what we say is if you want to get the maximum voltage transmission, the output impedance should be very small from the source, and from the load size, input impedance should be very large. So in order to simulate two scenarios, so I have drawn this circuit diagram here on capture sys, and I have already changed voltage to 10 volt DC and the load resistance, so that is 100 ohms, so we'll put it as 100 ohms, and rather having it R1, so I will change it to RS, so that it's kind of easy for me to refer it. And also the load resistor, I will change it to RL, and then the value of the load resistor. So now in this simulation, what we are going to do is to change this load resistor value while measuring power or voltage. So that is how we want to see whether we are achieving maximum power or voltage. For this one, we can add a global parameter. I will search here. We can search param PARAM and put that component somewhere here. So I have a global parameter. So this is what we call global parameter. So I have added a global parameter to this one, and then the value of this resistor, I need to change it. So you can put any variable type name here, but you need to put them within curly brackets. So I will put maybe R val. So it's the value of the resistor R. But this is a parameter now. So it's R val. So this is the one that we are going to change it, so that we will do with it this global parameter. Now there is a few things that you need to do in order to set this up. So first thing is you can double click this parameter. Once you do that, then you can add new property. So from here you need to add new property. So it gives you some warnings that you can't change it. Then parameter name, so that we put it R val. Then value of the parameter, for time being, let's say we'll put 1K, and we can put display on, so that will be displayed. And I'll click OK. And here it says whether to display, so I'll put name and value. Click OK. Some more warnings. Right. So we have already added this parameter, and we'll go back to our schematic diagram and see whether okay. So the parameter is there, R value is the global parameter, and default value is 1K. Let's consider maximum voltage transmission situation, so that we need to achieve maximum voltage over here. So therefore, to make the process easier, I will take a voltage probe and put it here, so that I'm measuring voltage at this point. And then I will create new simulation profile. And I will pick DC sweep in this case as well. But here the type of sweep, it's a primary sweep of course, but what I'm going to sweep is a global parameter, and parameter name is R val. So that's the same name that I have given, R val. And then start value and end value. So I will start R val with 0, and since I'm going to see the voltage, so end value maybe I'll put it as 1 tera ohm, and increment. So we can do it linear, but I'll go for logarithmic scale, so that it is much more logical. I will put 10 here, so that so I'll maybe start with 1. And I'll go 2, 3, 4, 5, 6, 7, 8, 10. After that, in the next decade, I'll go 10, 20, 30, 40, so on. Once I reach 100, then 100, 200, 300. So that is the idea of having logarithmic sweep. And each decade, I'll have 10 points. Right. So I have added a voltage probe, and then I'll run the simulation. So once I run the simulation, I'll obtain this one. Okay. What this curve says is, my x-axis is R value and my y-axis is voltage at RL. So we know that the voltage of the supply is 10 volts, and this is 100 ohm resistor, and we are changing this resistor value and see what the voltage that you can expect over there. So you can see that, so if the resistance is very low, like 1 to 10 ohms, so you are not even achieving 10% of that. But probably after 10K, maybe roughly about 20K, you are achieving 10 volts. So after that, it's getting saturated. So to be in the practical case, what we need is to achieve some accepted voltage, something like 100 ohms, so that we can achieve maximum voltage. Now, when it comes to achieving maximum power transmission, so we can consider the same circuit. So here I have written PRL, that is the power dissipation from this load resistor. So if we have the maximum power transmission, we should have to have maximum power dissipation from RL, because it's a passive device. So if you write the equation for that, we can write V squared over RL. So RL we have already calculated previous section. So it's this one and this one. Now, if you want to achieve maximum power transmission, now this expression is not as simple as the previous case. So if we want to find the maxima, we need to go for the traditional means so that we can differentiate power RL with respect to RL and we make it 0. So then when you solve the equation, you will get the result. So I'm not going to do it now. So if you want, you can do this one and find the maxima. So the maxima actually occurs when RL is exactly equal to RS. So in other terms, output impedance and input impedance has to be the same in order to achieve maximum power transmission. So when we want to find maximum power transmission, so we can use the same setup, but I will remove this voltage probe and I will put a probe to probe the power dissipation from the device. So I will tag this here so that I can monitor power dissipation, and then simulation profile I will edit it because from theoretical calculation I know that impedance has to be like equal in order to achieve it. So I will go for linear simulation. So I will start with 1 ohm and maybe go up to 1 kilo ohm, and increment in this case I will go step size of 1, and then I'll run the simulation and see what I can obtain from the results, and this is what I have obtained. So you can see clearly when I do the simulation, when I change R value from 0 to 1K, at 0.1K I'm reaching the maximum. So this is basically 100 ohms, right? So the 100 ohms, so that when you have the impedance matching, you are reaching the maximum. Okay, hope you understand this one. So this is what we call global parameter sweep, and we can do this kind of simulations very easily. Hope you got the idea. See you in the next video. Thank you.